you all to this webinar, and thanks for joining today's session. My name is Michele Merelli. I'm part of Particleworks Europe team, and I will discuss today about meshless CFD Particleworks for electric motor design. So the agenda of today is shown here. So first I will discuss why we need simulation and why we need meshless simulation specifically for improved e-motor cooling. Then we will see a full workflow of an e-motor or e-axle simulation, discussing all the tools, all the outputs we can get from the workflow. I will then present validation, some of the validation we collected in the last 5 years regarding temperature prediction or flow split inside, let's say, distributing channels and cooling channels of these systems. And then I will also give you additional references and invite you to the next events if you want to try the software itself. So let's first discuss motivation. Why do we need simulation? Why do we need meshless simulation? So as you are aware, I think electric vehicles are increasingly found in the automotive sector. We see the crazy growth of electric vehicle sales in the last 5 years. From, let's say, 2% of global fleet up to 16%, and this is only 2023. And at the same time, we see that requirements in terms of power densities, so how much power we integrate in this system, is higher and higher. And because of that, we need better cooling method for electric motors. So electric motors were first introduced, of course, and are used now basically in industrial settings where, let's say, the power density are not so high, because if I put an electric motor in an industrial setting, I don't care too much about weight. But as soon as I put the electric motor on a vehicle, of course, weight and power density becomes important. And because of that, also cooling becomes important. And that's why we see Particleworks used in the sector now. Conventional electric motors used air-cooled system or water jackets cool system to control the temperature in the electric motor, but as discussed, the performances are now much more higher in terms of power density, and we need better cooling. And one way to better cool this kind of system is by using direct oil cooling jets. So you see here an example coming also from a collaboration with TotalEnergies. We basically compare water jacket and direct oil cooling with oil jets. And here you see some jets coming from the rotor, actually. They could also come from external nozzles spraying directly to the most critical areas, such as the coils. And the objective here was first to compare the two methodology for the cooling. And what you see here are the results of the two, let's say, approaches in terms of temperature distribution inside the e-motor. You see the averages when we use direct oil cooling are, let's say, 8 to 10 times at 10 degrees Celsius colder. And you can see that coils, when we use oil cooling, are a lower temperature, and also the rotor shows lower temperature. And this is very important because inside the rotor we found magnets, we found sensible temperature sensitive materials. So this was a good first example of better cooling methods for e-motors. And Of course, together with that, the reason why we need simulation, or let's say why we see simulation more and more applied in the sector, is that it's not only, as we will see, because it's easier when we deal with meshless simulation, but also because computationally it's always and every year much more efficient. Particleworks runs on GPUs, and we all know how GPUs are improving thanks to AI, but then there is a spillover effect on other sectors, and thanks to the parallelization of Particleworks algorithm, we can effectively take advantage of this computing revolution. So let's briefly discuss about Particleworks and meshless CFD and the differences with conventional CFD. So here is a quick summary of and a comparison between conventional methods. It could be, let's say, mesh-based CFD solvers like StarCCM or ANSYS Fluent, and moving particle simulation, so meshless particle methods that are based on Particleworks. So instead of having to generate a computational mesh or simplifying the model for the simulation, we can directly work with the CAD and the complexity of the geometry and the rotations of the geometry. So complex coils can be easily modeled without any issue. Rotations of the rotor and the jets can be modeled, and also the spraying effect of, so the free surface flow of jets can be easily handled by meshless CFD. And that's why we see it more and more applied in the sector, because it enables simulation where previously was not possible. It's not only that, we also have a speed up in pre-processing, or let's say simulation preparation, as well as simulation times in running the simulation. As mentioned, we can run also on GPUs, and we can have good speed up. So overall, we are looking into 1 or few days of simulation workflow, complete workflow, compared to mesh-based CFD that required weeks. So here is a quick summary of the feature of meshless simulation. We don't have to generate a mesh, as mentioned, so the CAD can be used as its design. So we don't have to do simplifications. We can import it directly in the simulation, and then the simulation workflow is very easy. You don't have to be a wizard, a CFD wizard, let's say, and you can also run on GPUs. So it means you don't need big cluster or IT infrastructures for running these kind of simulations. So let's take a look at all the steps that we can integrate in a Particleworks simulation for an e-motor. So here is a summary of them. You can see that we can look into flow distribution inside the distributing channel. So here is a rotor with some cooling flow that then is distributed to certain nozzles. So we can look at the flow split depending on the operating condition. We can look at air simulation inside the e-motor. Here you see windage airflow type of analysis, and you can see one of the simulation possibilities for air integrated in Particleworks. Then what's usually done is to look at the oil distribution inside the e-motor, so oil accumulation and wetted areas, depending on the injected points, or again, operating condition, rotational speeds. The step farther down the line is then to map heat transfer coefficient and cooling capabilities of oil and air, and then apply it to, let's say, a thermal model that is also possible to do inside Particleworks to predict ultimately the temperature distribution inside the e-motor that is the most valuable output that you want to use and extract for this kind of system. So let's see step by step examples of the simulation outputs and results. So here you first see the air simulation, so windage effects inside the e-motors. We also take advantage of this multi-resolution region. So basically around the coils, we are also able to refine the air in order to have better flow through the windings and the coils. So here you see the simulation of air. You see in pink particles of air that are not refined, and I colored with the color map, sorry about that. And you can see only the particles refined around the coils that are colored in color map. I mean, I could also have colored the other particles, air particles, with the color map, but for the purpose of showing the difference, the different regions, I just pick this pink for the non-refined particles. But you can clearly see here air flowing through the windings in the transient simulation, and you can also visualize it with arrows. So with that, you can start to understand the flow and also the cooling capabilities of air for the e-motor. There is also an air gap here. It's partially solved. We can also look into air drag losses in the air gap, depending on the details we want to have in the model. And let's say, usually what is done is that this air field is then transferred to the oil simulation in order to take into account the effect of air onto the oil distribution. What you see here now is the second step, also taking advantage of a multi-resolution region around the windings. So as you can see on the right, we show only the smaller particles, let's say, that are refined in a better way around the coils. Here you see the full flow of oil. In this case, we have two inflows, static inflows and jets, and then one rotating jet as well. You might be able to appreciate that also here we are taking advantage of a multi-resolution, because inside this box we have smaller particle size because the nozzle is very small. I will show you in the next slide. But yeah, overall you see the oil distribution going through the windings and then floating down for gravity. So particles are bigger, smaller, then converted back to bigger when they exit the multi-resolution region that is, let's say, around the windings. And then you can see the accumulation of oil also at the bottom. And this is just an example of one result in terms of oil flow in an e-motor, oil-cooled e-motor. As mentioned, only smaller particles are shown in this visualization. So as you can see, when particles are converted back to bigger particles, so here, when oil goes to the bigger particles region, it's not shown on the right. As mentioned, I was also introducing a multi-resolution region in the nozzle area, and you see there particles with a smaller feature, and then the jet sprays to the windings. So there is a continuous conversion between smaller and bigger particles, discretizing the oil flow. And here you see only the, let's say, rotating nozzle particles accumulating on the windings, and then at the bottom of the e-motor. The next step in the simulation workflow is then to map, so project the fluid properties and the cooling capabilities of oil, for instance, on the coils. So you see here different examples together with heat transfer coefficient, we can map also the thickness of the film of oil or the average wetted time. So they have an understanding of where the fluid ends up and how good the cooling system is. You see oil flowing through the windings layers, and you can see accumulation and patterns of higher or smaller film thickness. So this is a very important feedback for designing or changing, let's say, the operating condition of the oil jets, or we can also look into how the oil properties can impact this kind of flow and impact the cooling capabilities ultimately. And then, as mentioned, these maps are applied to a thermal model. I just want to mention that the thermal model can be an external finite element model, but since the last release of Particleworks, we also have an integrated thermal model. So basically, you can run a finite element thermal model inside Particleworks and apply electromagnetic losses, but also let's say heat transfer coefficient maps directly to the same model. So the same model that you use for fluid simulation can be then, let's say, with a few arrangements and changes of boundary condition used for thermal modeling and temperature prediction. So here is an example of actually a coupled system where we have both fluid and thermal predictions, so solid temperature prediction. You see jets of oil cooling different elements of the e-motor, and we see also a coupled drive system. So this is effectively an e-axle where gears are cooled by the oil that is injected by the jets, but also splashed by indirect lubrication. So effectively, I just want to show you the full system here before discussing the results of temperature distribution. Here you see an example of coupled thermal and fluid simulation, where we look into oil jets, e-motor, but also lubrication and splashing of gears. Just to give you a full overview of the capabilities of the coupling you can achieve. And here is an example of temperature prediction inside Particleworks. We can see that we applied basically the cooling maps on the coils and on the other elements. We applied power losses to the model, and then the electromagnetic losses that were estimated with, let's say, an electromagnetic software. And then you can see again the cooling effects of the jets and the most critical areas, okay? And we can also see very interesting gradients in the coils. Everything here is done meshless also on the solid, because basically automatic Cartesian grid will be applied and discretized in the pre-processing of this simulation. So you don't have to give or to create a mesh also for the thermal solver. So it's very straightforward type of simulation. As mentioned here, we see the coupled drive with the temperature prediction on the gears and the coils and the flow of oil. Okay, let's now discuss validations of this method, because of course it's interesting to have a digital model, but it's also interesting to see correlation with experimental testing or thermocouples. So we have several examples. I will just discuss, let's say, the most important one, or the one that we think shows the most various type of application and validation. But I will also, let's say, collect at the end all the public material we have. So the first one is from the joint venture between NIDEC and PSA Group. It's the eMotors joint venture, and they discussed e-drive spray cooling optimization with Particleworks. So here is a system, is the full e-motor and the distributing channel they investigated. So in this case, we have also an inflow here, the flow split between a 2-rotor and 2-gravity circuit. So basically, oil is injected here, and depending on the rotational speed of the rotor, can go in a preferential or not way to the rotor side. Okay, so basically, one of the objectives here was to understand the flow split of oil between the rotor cooling system and the gravity cooling system. So basically, you can imagine here we have nozzles going directly, of spraying oil directly to the coils on the inner side, and then some nozzles, also static nozzle at the outer side of the e-motor. So as mentioned, the objective here was to understand if the flow split, depending on the rotational speed, could be captured as experimentally observed. So here you see the flow amount going to the rotor side as compared to the measured flow rate in orange. So you see that when we increase RPM of the rotor, we see in the measurements that the flow rate in the rotor increases, and this was captured by Particleworks simulation. Now let's discuss another very interesting presentation together with Riccardo. In this case, we wanted to validate the temperature distribution that ultimately, as mentioned, is the final objective. So the model is shown here. It's a similar e-motor. Here you see the maps of oil going through the windings and cooling the windings. And basically, Martin Brada, together with us, and the Riccardo paper that we can also reference later, at the end wanted to apply these maps to the thermal model and compare thermocouples results. So they have experimental results where they place thermocouples on the windings in 6 different locations, and they wanted to see the final thermal model and the, let's say, experimental results, how well they compare. The objective was actually to have a 5-degree gap between thermocouples and simulation results. And as you can see, for the 6 thermocouples, we actually achieve a much better agreement. We see that all points were matching the criterion, and the max gap between experimental and simulation was actually 2.8 degrees. So 6 different locations, we could see then a good 3D distribution of temperature and oil. And another example was discussed at our conference, Particleworks Experience, in 2023 by Gabriele Puccia at Polestar. And in this case, there were several validations. One validation was on oil flow visualization using a clear casing 3D printed prototype. So you see here the prototype, you see here the model investigated by Polestar, and I want to highlight that here we have an injection point on top of the stator. So basically oil is injected here, can flow through the stator and then spills down to the windings. So it's like a coupled, let's say coupled stator to windings cooling. So one objective was to understand if the flow, the transient flow, when we start to inject oil there, could be captured as compared to a clear casing. But actually, the other objective of this study was also to analyze the possibility of changing the sprayed oil around the winding. So you see here 3 configurations. So basically, we have some geometrical baffles, some variation of the e-motor, where we cover certain area, or we use solid elements to change the flow of oil coming from the stator. So you can clearly see here that oil can be collected on the outer side of the windings, or inner side, or actually in this case there was no protection. And because of that, we see different HTC maps distribution and also different losses, because of course oil can also go through the air gap and cause a little bit of losses. So the purpose was exactly that, was to test in less than 1 week several geometrical modification of this baffle to change the and optimize the flow of oil inside the e-motor. So it was found a trade-off between cooling capabilities and also churning losses due to oil entering the air gap. And then, as mentioned, they wanted to see the flow distribution of the transient injection in the stator. You see here oil injected on top, and then you see the transient behavior of oil. So of course, channels on closer to the injection point are filled in a faster way, and you see this oil distribution that is also matched experimentally. And you see also accumulation on the outer side of the e-motor, like so. So at 2 seconds, the flow distribution comparison was confirmed by Polestar and was in good agreement. So of course, I don't have time to discuss all the public material on electric motor improvements using Particleworks, but we have several, and you can find via the QR codes all the papers and the let's say examples and the complete presentations if you're interested. Here is some other examples. I will you will receive also a recording of this presentation, and you can then of course access these papers. I just want to mention that we have periodically introductory day on the method and on Particleworks. So if you are interested to activate a trial of the software and with our help understand if you can improve your R&D workflow regarding e-drive or electric motors, we have, as mentioned, monthly trial days. So if you're interested, you can scan the QR code and register to one of them, and you will have access to 1 month free trial and also our support in building such model, together with a short intro training day. So as mentioned, I could and I will discuss further, also depending on your questions. So, but for now, I think we cover most of the topics I wanted to cover. So let's maybe now open up the Q&A session. So I see there are already two questions. So Rock asks about the CHT results. So one question is about the interface between Particleworks and CFD code, and also if there are multiple simulation loops required to get the final temperature distribution. So let's see if I can address that. So as mentioned, those are the steps that are usually done. So the information about the cooling capabilities of air and oil can be easily transferred via CSV file, so text file, as boundary condition for the CHT temperature model. So we could have a coupled or a decoupled CFD to thermal model. So it depends. Sometimes we want to study the solid temperature after the fluid simulation. So it's what we usually saw and we usually suggest. So there is a transfer of information about boundary conditions from the CFD Particleworks result to the, let's say, solid solver, again, integrated in Particleworks. So there are, yeah, there's no loop, I would say. It's just a step-by-step simulation workflow, but done in the same interface and in the same, let's say, digital model, just changing some small boundary conditions, okay? So that's the advantage, because it's all meshless and it's all with the same interface, the same tool, and same digital model. I hope I answer the question there. So feel free to ask more if you want to have a better explanation to any of the topics we covered, or so the name it's covered. Payman asked about turbulence flow, and if we turbulent flow, if we compare it to shear stress at walls for particle compared to to regular CFD, and should the film thickness be much thinner? So turbulence flow can be modeled in Particleworks. There is a turbulence model inside and can be activated. There are some differences in terms of like a boundary layer between regular CFD and meshless CFD. So not all the concepts usually found in regular CFD can be applied to meshless methods. So let's say there are some slight differences again in the theory, in the numerics, but in general, yeah, we do have validation and comparison of the final results. So that is, I think, what is most interesting between mesh-based and Particleworks. Perhaps I could show you one other example of comparison with mesh-based. So this is another presentation we had from HPA Coxa Francesco Porta at our conference in 2020. So they compare for piston cooling applications, so slightly different application. They compare StarCCM with Particleworks in terms of heat transfer coefficient capabilities. So just jumping into the conclusion. So you see here an HTC map on the piston. So we see jets. This is the Particleworks results. And in the previous slide, we have StarCCM results of the jets and also the heat transfer coefficient on the piston. So here is a comparison of the HTC, and here you see for, let's say, a full rotation, a few rotations of the piston, the distribution of HTC between Particleworks and StarCCM, and you can see that there is good agreement between the two. But what was interesting is that Particleworks results were achieved in 10 times shorter times.